So, if you zoom into an iron cannonball at the atomic level, you'll find trillions of atoms arranged in a precise three-dimensional lattice, and this structure places each atom at a fixed distance from its neighbor, held together by what we call interatomic forces. So, you can imagine these forces as tiny springs that are incredibly stiff, and that is the reason iron feels so rigid. By contrast, in materials like foam or tennis balls, the atomic or molecular connections are looser or more flexible, giving them a soft or kind of a squishy feel. But the thing is that any rigid body, even ones made of steel or iron, are to some extent elastic. That is, their dimension can be altered a little by pulling, twisting, or by way of compressing them. So, take an iron rod that is, say, 1 meter long and attach it to the ceiling. And now, if you hang a large weight, say a car, the rod will stretch by maybe half a millimeter. That in percentage would be about 0.05%, and most likely the rod would regain its length of 1 meter if the car is removed. However, if you hang a larger car like this, the rod is very likely to be permanently stretched and would definitely not recover its original length if this car were to be removed. And if you hang a still larger car, the rod would first elongate and then rupture somewhere in the middle. So, if you apply a force on a solid, there can be three ways in which you can change its shape and therefore its dimensions. So, if you take this piece of cylinder and stretch it along its length, then you can see it getting deformed. Then you can also apply a force like this, that is a force perpendicular to its long axis, and you see it getting deformed quite like a book would if you applied a force in the same way. And this one might not be as obvious, where a solid sphere placed in a fluid under high pressure is compressed uniformly along the surface. But what is common between the three ways of deforming is the application of stress, which is defined as force applied per unit area of the object, that produces a strain or deformation per unit of dimension under consideration. And you'll understand this in a moment. So the stresses and the strains have different expressions in each of the three situations. But for most practical considerations in engineering, stress and strain are proportional to each other, and this constant of proportionality is called the modulus of elasticity. So that stress is equal to modulus into strain. Or in other words, for most ranges of deformation of a given object, the ratio stress by strain remains constant. So in a standard test where we assess the tensile properties, we subject a cylinder to a tensile stress by slowly increasing the stress from 0 to a point at which we can see a fracture on the cylinder. And the strain is incrementally measured and plotted. So what you get is a graph like this, that is a plot of stress versus strain. And what we can see in this graph is that for a significant range of applied stress, we have a linear relationship between the stress and the strain, and the cylinder can recover its original length if the stress is removed. So this equation describes this situation, that is, linear relationship between the applied stress and the strain. And when the stress is increased beyond this point, we see the cylinder does not regain its shape but is permanently deformed. And we describe this point as yield strength SY of the specimen. That is, beyond this point, this relationship ceases to exist. And if we continue to increase the stress, the cylinder will eventually rupture at a stress called the ultimate strength SU. And you see, these labels are quite well termed because at this point the specimen is kind of yielding but is not broken yet. But here it breaks, and therefore we call it ultimate strength. That is, it just cannot go beyond this point and breaks. So stress on an object is defined as force acting per unit area, and the force considered is perpendicular to the area A of the object. The strain, on the other hand, is the unit deformation, or more accurately, deformation per unit length, which then becomes a dimensionless quantity, that is delta L upon L. And you can also call it the fractional or percentage change in a length of the object under stress. Further, if the specimen is a long rod and the stress is below the yield strength, then not only does the entire rod experience the strain, but every section of it experiences the same strain when a given stress is applied. That is, you consider any section of any length, the change in its length to its original length would be the same across the length of the bar. Another thing to observe is that since strain is dimensionless, the modulus will have the same dimensions as that of stress or force per unit area. So, putting everything in a more formal way, we can say that the modulus for tensile and compressive stresses is the Young's modulus, and in engineering practice represented by the symbol E. Another point worth mentioning here is that even though the Young's modulus for an object may be almost the same for tension and compression, the object's ultimate strength could be different for the two types of stresses. So, as an example, concrete is very strong under conditions of compression, but quite weak when you pull it apart or put it in tension. And that is the reason it is never used that way. So this brings us to shearing stress, which is also force per unit area, but the direction of the force lies in the plane of the area instead of being perpendicular to it. And the strain here is the ratio delta x, that is this, by L, and the corresponding modulus is called the shear modulus, represented by the symbol G. So the equation for shearing becomes F by A is equal to G into delta X upon L. And the last type of stress is what we call the hydraulic stress. That, as the name suggests, is a stress due to the fluid pressure P on an object, where we know that P is nothing but the force acting per unit area. And here again the strain is a dimensionless quantity, but instead of change in length, we take change in volume, or the strain is delta V upon V, where V is the original volume of the object and delta V is the change in its volume. And here the corresponding modulus is given by the symbol B and is called the bulk modulus of the material. So this object, we can say, is under hydraulic compression, and the pressure due to the fluid is called the hydraulic stress. And remember that force always acts perpendicular to the surface. Also important to know is that the resulting pressure has no intrinsic direction. That is, the pressure on the surface of an immersed object is the same no matter how the surface is oriented. And that is the reason pressure is a scalar quantity, not a vector quantity. So here the equation can be written as P is equal to B into delta V upon V. So in case you go scuba diving, remember the physics. Your body is under hydraulic stress because water exerts nearly uniform pressure everywhere on you, squeezing you to a smaller volume. So it would be interesting to find what your personal B value or the bulk modulus would be.